With a couple of just announcement-ish things. So I would have graded your first problem sets here this morning. So you should check on your minor or dame to make sure that if you believe you turned it in, that you are marked for it credit-wise. I don't want it right now. I'll talk in a minute. If you had issues getting things done or getting it into OneNote or whatever, we'll have some time at the end of class and I can talk with you guys kind of individually, but this is going to be like a regular weekly occurrence. So we do need to kind of figure out, where the problems are and how to get your work, if you're going to do it on paper, into the OneNote and all of that kind of thing. The second piece is that some of us were pretty light in the amount of work that we showed in our homework. Some of us were just like list of numbers, like nothing else other than a list of numbers. I'd like to see a little bit more work than that on the things you turn in, even if it's kind of like a scribbly mess. That's okay. I'd rather see some evidence of like how you did the problem than nothing at all. Everybody okay with that? And if you're not sure if you did enough or not, you probably did. If it was more than just like a sheet of answers with no space, like no work to show with it. So we'll try to do a bit better on both those fronts for next Sunday. Remember, we already have 2 problems listed in next Sunday's problem set, 43 and 44. We're going to add some to that today, though. Everybody ready? I guess, one more thing before we get started onto the new stuff. Does anyone have questions from homework? At this point, you would have done up through 42, ideally. There may have been some things along the way that you weren't sure about. Josh?
31 through 34.
31 through 34. Okay. So the idea here on any one of 31 through 34 is that we're going to be, when we start asking for an exact value like this, we're going to be using a 30, 60, 90 or 45, 45, 90 triangles. So like if I'm doing sine of pi over 6, I want to find out whether pi over 6 is 30, 45, or 60. Those are the only 3 angles that I can do. I can find an exact answer for right now. So I'm just going to convert pi over 6 from radians into degrees. So I know sine of pi over 6 is the same as sine of 30 degrees. And then I'm going to draw my 30, 60, 90 triangle. And fill in the ratios. And then I remember sine is opposite over hypotenuse. So that would be a over 2a, which reduces down to 1/2. So there's my exact value. And that's all you need to do. Work the same way for the rest of them. Just, like instead of doing opposite over hypotenuse, you'll do whatever over whatever, depending on the true function. So the exact answer just means it's going to be a fraction, no decimal. So it might have a radical in it or whatever, but that's all we need. Yeah, no problem. Anybody else? Okay. Also worth giving you a little heads up. What haven't we done yet for this chapter that we're going to do for every chapter?
Quiz.
A homework quiz, right? At this point, you should have done all through 1 through 42. There's not a lot of chapter left. I'd expect to see a homework quiz here relatively soon. And if you're able to do the things that you did in the homeworks 1 through 42, should be no problem. Everybody cool? Just as a heads up that that'll be coming. Remember, they're surprise, but they're based on things you've done in the homework. Josh, is that a hand?
Easier notes to figure out.
No. Okay. Okay. So let's move on here to I don't have that open. To our next section. So just to put in context where we've been going, or what we've done and where we're still heading here in chapter 2. The goal has been to take our sine, cosine, tangent, these trig functions that we developed in algebra or in geometry that were tied to the right triangle, and try to redefine them so that we can do sine, cosine, tangent of basically any real number. So to this point, we've introduced this second measurement system for angles called the radian, right? We reviewed how to do right triangle trigonometry, sine, cosine, tangent, etc., inside of a right triangle. And last time we redefined how we measure an angle to allow us to draw an angle of any measure, right? That was called a standard position angle, where we put the initial side on the x-axis and we drew the terminal side rotating either clockwise or counterclockwise around the origin, depending on whether we're going positive or negative. Today, we're going to take these ideas, specifically the standard position angle idea, and work towards building out our new definitions of sine, cosine, and tangent, etc. All right. So let's say that we have some standard position angle. And on that standard position angle, we have some point P. That point could be anywhere on that standard position angle. So I'm just going to give it the arbitrary coordinates x, comma, y. And I'm going to give this angle the measurement alpha. So that little fishy is just the Greek letter alpha. Becomes typical in trigonometry when we start dealing with like points and sides and angle measures and all these things kind of going on at the same time. The convention is we use a Greek letter to define our angle measures, just so it's easier for us to keep track of what's an angle measure and what's a side length or a coordinate or something else. Everybody's okay with that? So alpha is the first letter in the Greek alphabet. Maybe you remember that from religion with I am the Alpha and the Omega. That's the first and last letters of the Greek alphabet. Anyway, that's beside the point. So if we look at this point on our terminal side, this point kind of defines a right triangle. Does everybody kind of see that? Now, what is the base of this right triangle going to be? Remind me again, how do we plot points? If I say plot the point 2, 3, what would your directions be? I think you mean the reverse though, right? Over 2 and then up 3. So if this is the point P here, the point XY, how far do we go over? X. And how far did we go up? Y. So the length of the legs of that triangle are going to be X and Y respectively, right? Everybody can hopefully seize that. What's going to be the length of the hypotenuse then? What kind of triangle do we have here? A right triangle. We know about the legs. What can we use to find the hypotenuse? The Pythagorean theorem. Excellent. So we can say that I'm going to name the hypotenuse with the letter R. So R is the square root of x squared plus y squared. And now that we've done this, what can we do? Well, if I know that sine alpha is opposite over hypotenuse, sine could also be written as y over the square root of x squared plus y squared, where x and y are just the coordinates of any point on the terminal side of our angle. Or more commonly, we just write that as y over r. So take this in for a moment on what we've just done. We've taken our definition of sine that was stuck inside of a right triangle. We've redefined our definition for sine to now depend only on the coordinates of some point on the terminal side of our angle. And because we can draw a standard position of angle of any size, we can now do sine of an angle of any size. We've just freed ourselves from the shackles of the right triangle. Now, making a similar construction, we can define cosine and tangent and secant and cosecant and cotangent and all of our other friends here. So this is our new definitions now for sine, cosine, tangent, cosecant, secant, and tangent and cotangent. Oh my goodness, look at this typo here. Now, you're probably looking at this and going, oh, Mr. Kulik, does this mean I need to remember a whole new set of definitions? I mean, not really. All I'm going to do is just think to myself, well, y is really the same as opposite. X is really the same thing as adjacent. R is really the same thing as hypotenuse. And really, these new definition is the same one. We've just changed out, instead of sides of a triangle, we're just talking about like relating this to points of a, on the xy axis. So like the x coordinate is just the adjacent side, the y coordinate is just just the opposite side. The r value is just the hypotenuse. Oh, so it's still like the same definition, kind of, right? Or the same format. We're just doing a little translation. So let's see, we have this, we got this, got this, are kind of our keys that we need. Let's do an example here. So let's say that we have the point -3, 4, and that lies on the terminal side of some angle theta. We want to find the values of all 6 trigonometric ratios for that angle theta. So I'm going to start by drawing a picture. So the picture I'm going to draw is going to be the one for my standard position angle theta. So there's my initial side. The terminal side needs to go through the point -3, 4. Is everybody okay with how I've drawn my picture here? Okay. So before I begin, I note that I have x, I have y, but I need r. I remember that the formula for r that I gave was x squared plus y squared. So -3 squared is 9. 4 squared is 16. 9 plus 16 is 25, and the square root of 25 is just 5. And now I can go ahead and just use my new definition. So I know sine theta is y over r. Well, y is 4, and r is 5. So 4 over 5. Cosine theta is x over r. So x is -3, r is 5. Tangent is y over x. So that's going to be y is 4 and x is -3. And then the definitions for cosecant, secant, and cotangent, I don't really remember those. I just remember that they're reciprocals of sine, cosine, and tangent, respectively. Yeah, Joey? Sure. So cosecant is the reciprocal of sine, so 5/4. Secant is the reciprocal of cosine, so -5/3. And cotangent is the reciprocal of tangent, so negative 3/4. So those are my 6 answers. What do you notice here that's happening that we've never seen happen before? Is that the values of sine, cosine, tangent, etc. might be negative, right? We've never seen that happen before. Is that okay? Yeah, it's okay. And in fact, we can predict what sized angles are going to give us positive or negative values of sine, cosine, and tangent. All right. So remind me, in the first quadrant, our x and y's, are they positive or negative? Which? They're both positive, right? So because I know that r is always positive, like r is a distance, right? It's the distance between the origin and that point on our terminal side. All of our trig ratios have to be positive here, right? So the way I remember that is just the letter A for all. In the second quadrant, x is positive or negative? Negative. But y is positive. So all the trig ratios that include an x have to be negative, right? Because the other parts are positive. So those were cosine, tangent, secant, and cotangent. Those are negative, but sine and cosecant were positive. So I'm going to remember that just from the S from sine. Well, let's actually write it. Let's write that. S from sine. So far, so good. Okay. In quadrant 3, x is positive or negative? Negative. And the y is negative also. So any of our ratios that have just one x or y are going to be negative. So that would be sine, cosine, cosecant, and secant. Tangent and cotangent will be positive because you have both an x and a y in there. Negative over negative cancels to make positive. Oops. So I'm going to remember that quadrant with t for the tangents, again, the positive pieces. And then in quadrant 4, x is positive or negative? Positive, but the y is negative. So anything with a y coordinate in it is going to be negative. So that means sine and tangent and cosecant and cotangent are all negative, but cosine and secant are positive. I'm going to remember that with the letter C for cosine. It's pretty messy even for you, Kulik. So anytime the terminal side of my angle lies in, say, quadrant 4, I know that cosine and secant will be positive, but any of the other 4 trig functions are going to be negative, just by the location of that terminal side, right? The way I remembered this when I was a student in your shoes, I remembered all silly turtles crawl was what they told me when I was a student. And again, the A for all tells me all the trig functions are positive. The S in silly tells me that sine is positive, and so is its reciprocal. The T for turtle tells me tangent is positive, and so is its reciprocal. And then crawl, the C in crawl tells me cosine is positive as well as its reciprocal. So that's the way that we can predict which trig functions will be positive or negative. All that we need to do to figure that out is know what quadrant the terminal side of our angle lies in. And likewise, if I am told that, say, where is sine positive but cosine negative? If I give you 2 of the 3, you should be able to identify what quadrant does the terminal side of our angle have to lie in. So if sine is positive, I know we're either in quadrants 1 or 2. But cosine's negative, so I know I'm in either quadrants 2 or 3. The only place where both those 2 things were true was in quadrant 2. Do you guys see how I did that? So you can use it to go the reverse. If you know information about 2 non-reciprocal trig functions, you can, or at least whether one's positive or negative, you can tell what quadrants we're dealing with. Does that feel okay? Josh? Sure. Okay. Let's go back and let's do another example. So let's say we want to find cosine of 150 degrees. Notice here they didn't give us the coordinate for the point, right? Well, that seems odd, Mr. Kulik, but okay, let's give this a shot. I'm not sure how I'm going to use my new definitions to do this, but, you know, like Mr. Kulik's told me a bunch of times, let's start by drawing ourselves a picture. So 150 degrees, we have 90 degrees that'll get us through the first quadrant, and then like 30 degrees more, right? So that angle right there must be 60 also. Is everybody good with that? 30 and 60 are complementary, or 150 plus, oh my goodness, Mr. Kulik, you dope. That's not how that works at all. Okay, So I did 90, and then I did 60 more to get over here. Goodness gracious, great googly moogly. All you guys should have been yelling bloody murder at me. Like, but Mr. Gulick! I'm embarrassed for all you guys. Do that. So we have this, right? I'm just going to pick some point on my terminal side. And just like we did before, I'm going to make like my right triangle. And aha! I notice something magnificent has happened. That's a right triangle, and one of the angles is 30 degrees. What's the other angle got to be? 60. And what does that tell me then? We have a 30, 60, 90 triangle, right? Woohoo! I'm just going to draw that 30, 60, 90 triangle a little bit bigger over here. So I have some space. Is everybody okay with me just rewriting it on the side? If you drew big, you probably don't need to rewrite it. I have a bad habit of like drawing the tiniest picture possible and then realizing that like, oh, I got to add a bunch of labels to this and now I'm in a lot of trouble. All right, so I'll draw in my ratios, just like I would. But there's one little problem. Does anybody see the little problem here? It's tough because it's like a geometry problem. What quadrant is the terminal side of my triangle ending in? Ends in the second quadrant, right? What do we know about the x-coordinate in the second quadrant? It's negative. Which side of my triangle represents that x-coordinate? It's that side, right? So it really, that side, I'm going to put a negative sign on. And now you're going, Mr. Kulik, how do I have a negative side length on a right triangle? You have to remember that this is not really a triangle that we're drawing. This is just representing the points, right? That this is like the x coordinate here. This is the y coordinate over here. And this is like the distance to the origin over here, right? This is not actually a triangle. It's just a convenient representation for us. Is everybody okay? Okay. The most common mistake students will make is forgetting the negative signs. That's why I'm taking it slow and pretending to be a little bit, oh, look at it, I didn't know. I knew, but I'm hopefully turning it into a story, and the story you'll remember when you actually have to do it on your own. It's easier than just being told if you have a little story to go along with it. Or like, oh, there's a mistake here. Mr. Kulik warned me about this. He's still warning me about this, so it means it's probably pretty important. It's pretty important because 2/3 of us will make this mistake the first time we do this and be like, why is this wrong? Be like, I warned you about this mistake in class. I spent 5 minutes just talking around in circles where you're like, can we get on with it? And I was like, no, I want to talk around in circles some more so that when it comes to this mistake, you'll remember me telling you about this being a very common mistake. Okay. So now that we have this, let's do cosine of 150. So this point here could be negative a root 3 comma a, right? Where the radius would be 2a. Everybody's okay with what I did there? Again, I'm just taking my values from the triangle that I drew just on the side and just rewriting them again. Doesn't matter whether I use x over r to write negative a root 3 over 2a, which reduces down to just negative root 3 over 2, or if I did cosine 150 equals opposite over hypotenuse, and I use the picture that we drew before, they're both going to give me the same result, right? Because they mean the same thing. Because equivalently, what we've done is we're just translating back and forth between our definition, our point definition for sine, cosine, and tangent, and our right triangle definition for sine, cosine, and tangent. We're just kind of bumping back and forth between those and putting in a context that's easy to use. So this problem where we didn't give a point, I wanted to try to create a right triangle and go back to, our right triangle definition. In the case where I am given a point, I'll stick with the point definition and just go straight to my answer, right? So far, so good? Yes, sure. Okay. Ready for the big finish here? Because we can do a little bit better than what we've done with our definition. Okay? What part of this definition still feels like you're giving me a lot of freedom here? Can we standardize this process just a little bit more? That place where we're given some freedom is where we're picking that point P, right? P can be anywhere on that terminal side, right? You have infinitely many choices. As long as it's on the terminal side, well, it can't be at the origin, but I don't think anybody'd be like, that makes an angle. It's pointing right on top of it. But any point on that terminal side is okay. But what if we just standardize how we pick that point, P? What if we pick it the same exact way every single time? Maybe we can even make these. Where did my thingy go? There we go. Maybe I can make these definitions even a little bit neater than they are right now. Not that they're bad, but what if they get better? Okay. So the way that we're going to do that so if we standardize that choice of P, we're going to standardize that choice of P so that it's exactly 1 unit from the origin every single time. So if we collect all our possible P's for every possible angle, what is that collection of P's going to be? If I take every possible P from every possible angle, what shape are we going to create? A what? Did somebody whisper? A circle! That's exactly right. A collection of points that's all 1 unit from the origin. is going to be a circle. That's all 100% correct. And in fact, the radius on that circle is 1. So we call this a unit circle. The unit implying that the radius is 1 unit of length. So if we do this, then so for our unit circle definition for sine, cosine, and tangent just becomes, all right, well, we have, let's just put it, okay, is just this, where y is the point on our unit circle, or is the y coordinate on our unit circle. X is the x coordinate for our point on our unit circle. What happened to the over r part from before? What's r equal? 1. So y over r just becomes y over 1, which is just y. Notice that tan theta and cotangent theta didn't change. They're still the same because neither of those definitions depended on r. But the rest of our definitions, sine, cosine, cosecant, secant, are the same as before, just in place of r, we've written 1.
Are these not the same ones as before?
Correct. So they are slightly different because everywhere there's an r, we've written a 1. Now, in trigonometry, we're going to be particularly interested in finding exact values for like sine of theta, or cosine theta, or tangent theta. Right now, the only angles we can do that for are going to be ones where when we draw the angle and we draw that little reference triangle afterwards, where that reference triangle is either a 30, 60, 90 or a 45, 45, 90 triangle. Okay with that? To make our lives easier, rather than having to draw these triangles every single time, we're going to collect that all that information into one place. That one place is called the unit circle. And it looks like this. I'll have a copy of this for you next time to give to you in your hand. There is one in OneNote, but I'll print off a copy for everybody for next time so you don't have to like keep jumping back and forth between pages. And now you look at this and it looks really overwhelming, right? But this is how we use this. Let's say we wanted to do sine of 210 degrees. I locate 210 degrees on my unit circle, and I know my definition for sine is y. So sine of 210 is -1/2. I don't have to draw the triangles. I don't have to label opposite over. I don't have to do any of that. I just look it up off the unit circle. That's what the unit circle is here for. It's just a way to make these exact value calculations simpler. Say I wanted to do tangent of 390. Whoa, Mr. Kulik, 390 is not on the unit circle. You're right. but 390 is coterminal to an angle on the unit circle. What angle is 390 coterminal to? If I subtract 360 from 390, I get 30. So if I go to 30 degrees, tangent is y over x. So I'd end up with 1/2 over root 3 over 2, which simplifies down to root 3 over 3 after I reduce and I rationalize my denominators. I did that in my head. You're not expected to be able to do that in your head. I reasonably expect you to need to write some stuff down on that, but you can trust me on that. What do you guys think? We see what the power of this thing is. Allows us to get these exact value calculations, things that you can't get off of your calculator, basically for free. You just need to be able to read this and use this. Is that okay? All right. Okay, one more thing I want to do before we can be done for today. God bless you. Oh, those are coughs. Never mind. I rescind my blessings. We only bless sneezes in this school. Coughs. I hope you feel better. Now you have a drink of water there. All right. Our last example here, it says to find sine theta if cosine theta equals 5/7 and cotangent theta is less than 0. So there's really going to be like 3 steps to kind of doing this. The first step that I need to do is figure out what quadrant the terminal side of my angle lies in. So I see that cosine theta is positive. So if I do my all silly turtles crawl, cosine theta is positive in A for all and C for cosine. Everybody's okay there? And cotangent being negative, well, that's really the same thing as tangent being negative. And tangent is negative. Well, tangent's positive in T and in A, so it must be negative over an S and C. So I know that my terminal side of my theta has to lie in quadrant 4, where both cosine is positive and cotangent is negative. So now that I have this, I can go ahead and draw a picture. So now I'm going to start trying to get towards my answer for sine here. So I know cosine theta is 5/7. And I remember my point definition for cosine tells me that cosine is x over r. So I know that x is 5 and r is 7. Everybody's okay with that, I hope. Now, I know then that point P, the x-coordinate is 5. And I know something about its y-coordinate. What can I say about the y-coordinate for point P since we're in quadrant 4? Since we're in quadrant 4, the y-coordinate must be negative. I'm going to draw that in right now. And my last step here to be able to do sine, which is just y over r, is I got to figure out what y is. So I know that x squared plus y squared is equal to r squared. So I know 5 squared plus y squared is equal to 7 squared. 5 squared is 25. 7 squared is 49. 49 minus 25 is 24. And if I square root both sides, I get y is plus or minus 2 root 6. I simplified that radical in my head. If you can't do that in your head, that's okay. Certainly write it out by hand if you need to. It's not an expectation that you'd be able to do that in your head. Right? 24 is 4 times 6. Square root of 4 is just 2. So you have 2 root 6. And I know that I want the negative. We already decided that. So my y-coordinate is negative 2 root 6. And now I'm finally ready to get my final answer. Sine is y over r. So it's negative 2 root 6 over 7. So the first piece is going to be to draw the picture. The next step will be to solve for the missing either coordinate or r, depending on what it is you're given. And the third part would be, now that you know everything, just plugging the results into your formula, into the right formula. How do you guys feel? This is a lot today. We did a lot of things today. So what I'm going to have for us to work on is today, I'd like you guys to work on the point on the terminal side definition problems. So that would have been like 45 to 50. And I also have a delta math covering this same topic. Next time, we're going to work on the unit circle definition problems. So that's whatever, 51 to 60. And I have a worksheet for us to work on that as well next time. And what else might happen next time? Oh, that homework quiz still is hanging over here, but there's not a lot left because this was the last section in chapter 2. So in addition, expect a test next week. We'll have a review day and talk about like what to expect for that. I don't know if I mentioned this on the syllabus day, but for all of my regular math classes, as part of your review day activity, you can make a half sheet front and back of notes, anything you want to put on there that if you turn into me on that review day, I will give it back to you on the test day for you to use on your test. Okay? The one caveat is you have to be present on the test day to be able to use your sheet of notes. If you're absent on the test day, you can't use your notes. So you have to, it's an attendance bonus, but it's a pretty good bonus. You put on there whatever you want, example problems, notes, whatever. I'll tell you the things that I'm going to give you formula-wise, but anything else that you're like, ooh, I don't think I'll remember that, or I want that all silly turtles crawl thing on there or something, like, put on whatever you want. Okay? How do you guys feel? It's okay? Clear as to what we're going to do? Yeah? Okay. So just to show you what the delta math looks like. Again, I think that sometimes it's nice to just see an example before trying to get in here. So I have a bunch of them. So the first one is just saying, what quadrant does it lie on if sine is positive and tangent is negative? Well, sine is positive in 1 and 2. Tangent is negative in 2 and 4. So that has to be quadrant 2. So I answer and we're done. It's just an all silly turtles crawl problem. Same thing here. Cosine is positive. Is negative. So that means we're in quadrants 2 or 3. Cosecant is positive. That's the same as sine being positive. So that's 1 and 2. So we're in quadrant 2 again. So the only difference between the first two is that, like, you'll get any of the ratios instead of just sine, cosine, tangent. You can get other ratios there. So here it says, here's the value for cosecant. And we know A is in quadrant 1. So you can just label your, like, R, X, and Y and just solve for the missing piece in order to determine the value secant A. Is that okay with you guys? Just like we did in that previous example, but it's easier because it tells you where the terminal side is, right? So you know the signs immediately. Same idea, but this time you might get something other than quadrant 1. So you have to watch your signs there. Same idea. This is just like the example we gave, right? I gave you a point and then ask you the value of something else. So again, you can just use your point definition. And then here it asks you to draw your angle and standard position and then find the exact value. So you're going to be drawing like a 30, 60, 90 or 45, 45, 90 triangle for the given ratio in simplest form with rational denominator. So same idea. Is everybody okay with what to do here? Very much like the examples we did, right? Nothing cuckoo crazy here, but if you're stuck, feel free to come up and talk to me about stuff. Nothing's timed this time, though. Yay! It's cool. Like, I hate the timed ones. It just makes me nervous. It's good practice, though, guys. Okay.
So can I put this right here for a second?
Yeah, absolutely. Now, did you take any pictures of the homework yet?
No, I couldn't figure out how to take a photo for some reason.
Do you have your cell phone with you? Can you grab it? I'll show you.